Then I will talk a bit about wind turbine simulations use the actuator line method. It's a bit different from what Mosen and Rodolfo showed in the meeting before. It's a collaboration between AGLRS here from the University of Stuttgart, University of São Paulo, and University of Twente. I will talk first a bit about the challenge, then the HPCWE use cases where our work fits in the HPCWE consortium, then about the validation of the actuator line model and also the validation of this model under unsteady turbulent wind conditions, and then end up with a small summary. So the challenge of this wind energy sector is the different scales that we have. First, we have this mesoscale to microscale scale that we can have some domains of around 50 kilometers down to 3 kilometers. That's where the wind parks are placed. And then when we zoom in, then we have the individual wind turbines. That's about 300 meters. Then we have the blade dynamics, where we have individual blade that's around 100 meters. And then we have the cord of this blade that's around 1 meter. And then we have the materials that made these blades. And we have all this together. That's very different scales and different methods to tackle them. In the first series of our internal meetings, we had presentations about this mesoscale to microscale simulations from the TU. And today I will show you something about these wind turbine simulations. In HPCWE project, we have 3 use cases that are divided in 2 main applications. The first application is the efficient use of the HPC resources in the simulation of flow around 1 wind turbine. That's for the use case 1, where we will validate our algorithms and codes for this application. We have this high fidelity fluid structure interaction that was object of the prior presentation, and we have the aerodynamic wakes of wind turbines and wind farms. That's what the subject of my presentation. And we also have this effective scale integration in wind energy beyond the state of the art. That's object of use cases 2 and 3. For this use case 1, the flow around the 1 wind turbine, we are interested in the wakes of these wind turbines and wind farms. And these wakes and their interaction are better represented by large eddy simulations. So like the one from this video that we are saying. And these unsteady simulations that are needed for the large eddy simulations need special wind boundary conditions due to the turbulent structures. I will show more about it in a minute. But the computational cost of resolving the whole blade geometry is prohibitively large using LS, as the colleagues have already mentioned. That's why we use a different approach. They use the actuator line method, where the turbine blades are replaced by the influence of the main flow. Then the forces of some segments of the wind turbine blades, the blade elements, are included as source terms in the equation of the conservation of momentum. I will introduce a bit more about it in a minute. Then today I will show you 2 works that we are developing. The first one is the validation of the actuator line model itself. And a second study is the validation of this actuator line model under unsteady turbulent wind conditions. I I will show results using 3 different software packages. The first one is Wing3D. That's an open source code developed by ICL that's based on Xcompact 3D. It's a finite difference method that shows a very good scalability beyond 100,000 ranks. It's high order, so 6th order discretization in space and 3rd order in time, and we use then the actuator line model. Then the U20 LAS, that's developed by our partner Uni20. It's pseudo-spectral code in the streamwise and spanwise directions, and 2nd order in the vertical direction. Use the second order time discretization, and also implement the actuator line model. And the 3rd package is OpenFOAM with the Turbines foam plugin, where it's an open source program, so both, so the OpenFOAM and the plugin that use the finite volume method, but has not so great scalability. So it scale normally good up to 5,000 ranks, more or less. It's 2nd order accurate in space and time. And we have various models that we can use, actuator line or actuator disk or single CP models. It's very flexible. Then I will start with showing the results of our first collaboration. That's the validation of the actuator line model, where we do a cross comparison between Wing3D and U20 LAS. We use the actuator line model and different smearing functions. It's a collaboration for Lukin Liu and Michelle Stevens from 20, Daniel, Lucas, and Bruno from USP, and myself from HLRS. Then a bit about how the actuator line model works. So then a blade of a wind turbine is divided in some sections, and each section is located at a spatial position. And at each of these spatial positions, a volume force is applied in the solver. This aerodynamic force, it depends on the coefficients of, here it's normal and transverse velocity forces, but it can also be lift and drag forces, and it depends naturally on the velocity at this specific point. But to apply this force on the numerical solver, we need a smearing function. That's usually a Gaussian. Here we see that's the usual Gaussian projection that we have. And this exponential function is computationally expensive. And one of the objectives is to replace this function using another approaches to save computational time. We use the NRL 5 megawatt wind turbine for the comparison. We have an uniform inflow with 8 meters per second, and we have a large domain where we solve the actuator lines from these blades. Then here are some results for the intermediate grid resolution. The grid sizes are approximately 5 meters with 9.4 million elements total. And each point that we see here in the graphs represent one of the blade elements. Then we see that for this intermediate grid resolution, the results fit very well. So we have a very good comparison between the Wing3D using the exponential function, this Gaussian function, the normal one. Wing3D using the compact version that was developed by the colleagues from 20, and also the 20 LAS solver. And also CP and CT have a very good approximation between two codes. When we talk about the computational time or the computational efficiency, so the compact mirroring function that we are testing shows a small advantage in computational time in comparison with the normal Gaussian function. Although the overall computational time is very similar between the two versions. And to understand also a bit more about this computational time, I'm studying the influence of the actuator line model on the computational time on one simulation, and I'm seeing that strongly depends on the grid size per rank or per core. That leads to our graph here at the right-hand side. We see that here we have grid elements per rank, per core of the machine. And the blue line shows that with a small amount of grid elements per rank, I can solve the most elements per second. That shows me that the efficiency of the code is very high when I have less elements per core, which is expected. If I have a very less elements per core, I can better use the cache memory of the processor, and the processor has less work to do, and then I expect a better efficiency. But using the actuator line model, we see here in orange that up to a point I have a good computational efficiency, but if I decrease the grid size, then my efficiency drops. That's expected because the actuator line model is not parallelized in the sense that I cannot distribute the work of calculating this of calculating CL and CN over mirror processors, but it's an indication where we should concentrate our efforts in the future. So again, it's an ongoing work, but our conclusion so far is that Wink3D and U20LS produce similar solutions for the intermediate range of mesh refinement, and that both Gaussian and compact mirroring functions produce very similar results, which shows the robustness of the method. And the computational performance is similar when use the Gaussian and compact functions. Now we move to the second set of results. Now it's the validation of the actuator line model under unsteady turbulent wind conditions. And why it's important. So we know that the power generated by a wind turbine responds non-linearly to the incoming wind speed. And that even in short periods of time, the variability of the wind speed can have a significant impact on the power. To tackle this problem, special boundary conditions have been developed for OpenFOAM, where the incoming mean wind velocity that follows a logarithmic atmospheric boundary layer profile varies in time following a prescribed input. And then synthetic turbulent structures are added to the mean wind profile using a synthetic inflow turbulence generator. What I mean with that, so for this validation, we use real data, so data from the Swift benchmark case, which is included in the International Energy Agency Wind Task 31. They have a meteorological mast that measures the velocity, the incoming velocity of the wind in several heights. And then they have also information about the wind turbine power, and also they measure the velocity in the wake. Today I will show you results using the power of the turbine. And here we see an animation of the simulation using Wink3D. But it's similar when I'm using OpenFOAM. Here we see these measurements from the Swift benchmark. They have a series of 10-minute measurement runs For the neutral atmospheric conditions, they have 6 runs that we are seeing here, the right-hand side size, the velocity, and here's the time, 10 minutes, 600 seconds. The unsteadiness of the wind speed is clearly seen. So for some runs, for example, this run 4, the velocity is more or less constant. But for example, for the run 0 that we have here on the top, we have some periods of time where the velocity is very low, below 6 meters per second, and some periods of time where the velocity is over 10 meters per second. And we see that these fluctuations or this variability is not turbulent in nature. The turbulent is very high frequency. We see here for the zigzag of the velocity measurement. But they show this, we see these low frequency fluctuations that can alter the power output of the turbine. Then to include this information in the simulation, one of the runs was selected, this run 0, that shows a large variability of the mean velocity. And this wind data was filtered using a 10-second window, and this time averaged velocity that we are seeing here in the blue line was used as the input for the LS. And to separate the turbulent fluctuations from the low frequency variations. Then the simulations took this time averaged velocity and included the turbulent structures using the turbulent generator. Here we see an animation of the simulation using this variable wind speed. So there is OpenFOAM LAS simulation. A grid has 11.8 million elements. It's very refined in the region of the turbine. And the structure, the turbulent structures are generated using a synthetic turbulence generator. We see the isosurface of the first intem of the actuator line model that represents the blades of the turbine. And we see that the wind turbine rotational speed varies with the incoming wind, as it's expected from a wind turbine. And we also see here at the right-hand side how the turbine power varies with time. We see, for example, here by 250 seconds. I will stop the video here, where we have the lowest, oh, sorry. When we have here, we have the lowest velocity, wind velocity, that we see that we have more yellowish colors by the contour plots at the left-hand side. And we have also the smallest turbine power. Then when we move to a region of high wind speed, here the mean wind speed is 9.5 meters. Then we see the red color on the contour plot and also an increase in the turbine power. Then I will show the same simulation, but using a constant mean velocity. We see here that naturally the turbine power fluctuates, but it fluctuates around a mean value, as is expected, as the velocity also fluctuates around a mean value. And in this case, the wind turbine rotation speed stays mostly constant because it responds to the incoming wind speed. And again, this is also an ongoing work, but the results that we have so far indicates that the simulation using a constant velocity profile predicted a turbine power that's 2% below the measurements. And using the variable incoming wind speed, the results improved shown significantly, and the predicted turbine power deviation dropped to around 0.02%. Is almost correct. Both numbers appear to be low, but the fact that even a high fidelity simulation can carry a 2% error only by assuming a mean velocity speed over a period of 10 minutes, as it usual, it's of great importance to the predictions for wind turbines and also for the wind parks when in the future. Now we come to the summary to see that HPCWE is promoting the use of this high-performance computing in wind energy in both Europe and Brazil, that we've seen from our collaboration, that we have different countries, Brazil, Germany, Netherlands, UK. And our efforts are mostly included in use case 1, that deals with the wind turbine simulation. We work in the Actuator line models, validation and enhancement, and also in the computational efficiency for large-scale runs. So thank you very much for your attention, and I'm open for questions.